My name is John, and over the last 6 weeks, I've been working with faculty to improve demand forecasting methods. We all know that predicting the future is hard, but accurate predictions are essential for organizations across sectors to plan ahead. Retailers need to project demand for their products, banks and investment funds want to know future values of stocks, and public health organizations like the NHS need to estimate future numbers of COVID cases around the country. And with better forecasting tools, retailers can accurately serve demand for their products, banks and investment funds can maximize their profits, and the NHS can plan hospital capacities to save lives. At faculty, we are developing demand forecasting tools to be used across industries. Surprisingly, deep learning is not the go-to approach for this. Instead, statistical methods provide reliable and competitive baseline models that often work in terms of interpretable, seasonal, and trend components. While deep learning has been applied to demand forecasting, the performance advantage is often not clear, and overall, deep learning has not transformed the field of demand forecasting in the same way as computer vision or natural language processing. So for this fellowship project, I investigated a way to combine the best of both of these approaches. And the paradigm I explored for this is self-supervised learning. In self-supervised learning, we train models to perform predefined tasks for which labels can be generated automatically. In this process, the model learns useful representations of the underlying structure in our data, which can be utilized later on. Let me illustrate this with an example. Say I have a set of images. I can define the following task. I chop up my images and permute them. I then train a machine learning model to undo this permutation. By training the model on lots of different examples, it learns useful representations of image data. For example, for this picture of a cat, it has to recognize the different elements of a cat's face, such as the eyes, the ears, and the whiskers, and it has to learn that they fit together in a certain order. Later on, we can take new input data and reuse parts of our trained model to construct the data representations. These representations are valuable input to other models that we build on top of them to perform different tasks. So for example, we could then easily go on to build a classifier that discriminates between cats and dogs. To apply these ideas to demand forecasting, we need to adapt them to work with time series data. A time series is simply a sequence of observations recorded over time. For this project, we focused on two important features of time series: the trend and the seasonality. For the trend, we came up with the following self-supervised learning task. We extract two chunks of the same size from the time series and predict the distance between them. To learn weekly, monthly, or yearly seasonal patterns, we implemented a permutation task. For example, for a week of the time series, we mix up the weekdays and then train the model to reconstruct the original pattern, thereby learning what a typical week looks like. In our overall workflow, we start with our time series data and then learn either seasonality or trend representations. These representations are input to a forecasting model that we build on top, which is then validated on a separate test set. For both seasonality and trend, we were able to successfully train models to perform these tasks. And our seasonality representations outperform non-specific input encodings when used in downstream forecasting tasks, showing that they extract useful information about seasonal effects. While we were able to train trend representation models, we are still working on using those representations in forecasting. So to summarize, I introduced a promising new approach of using deep learning for demand forecasting problems. I researched self-supervised learning tasks for time series data. The representations of seasonality and trend developed in this project can be passed to statistical models to combine deep learning and statistical methods in demand forecasting. And finally, I built some tools and code to use as a basis for future work in this area. Thank you for listening.